Hey everyone, and welcome back to CodeAccessHub. We're jumping right into part 4 of our big series on Ilya Sutskever's top 30 fundamental AI papers. And today's topic? Oh, it's a real mind-bender. We're getting to the very heart of what information even is, thanks to a paper that introduced the world to Kolmogorov complexity and algorithmic randomness. Buckle up, this is going to be fun.
Okay, so let's kick things off with a question that, well, it seems super simple on the surface, but it's actually one of the deepest questions you can ask. What is randomness? I mean, you and I, we have a gut feeling for it, right? We know it when we see it, but can we actually measure it? Can we come up with a rock-solid mathematical definition? Well, that's exactly what we're going to try and do. All right, take a look at these 3 strings of ones and zeros. Just go with your gut. Which one feels the most random? I bet your brain is already picking up on things, right? Some of these just feel like they have a pattern, and others look like complete, total static. The real question is, how do we get past that feeling and put a number on it?
So let's zoom in on 2 of these. Look at string A. It's painfully obvious, isn't it? It's just 0, 0, 0, 1 again and again and again. You could tell your friend how to write this entire thing out in what, 5 seconds? Now look at string B. What's the pattern there? It's just chaos. It's what you'd get if you flipped a coin a bunch of times and wrote down the results. There's no shortcut, no simple rule. It's just stuff.
So how do we build a bridge between this super predictable string and the completely chaotic one? We need a really big, really powerful idea. And that idea is all about defining information not by what it looks like, but by the power of a computer program. This is where we introduce the star of our show today, Kolmogorov complexity.
Now, here's the big, game-changing idea. The Kolmogorov complexity of a string isn't about the ones and zeros inside it. It's about the shortest possible description of that string. Let's think of it like a recipe. What's the absolute tiniest, most compact recipe, or, computer program that you could write to generate this exact string of bits and then stop? The length of that tiny program, that's its complexity.
So let's go back to our simple string, the one that's just 0, 0, 0, 1 over and over. The recipe for that is ridiculously short, right? You just write a tiny bit of code that says, hey, computer, repeat 0, 0, 0, 1 2,500 times. See, you can take this massive string and squish it down into a tiny little description. That, my friends, is the definition of low Kolmogorov complexity.
But what about our random string, the one that looked like coin flips? Is there a clever shortcut, a simple loop? Nope, there's nothing. The shortest possible program to create that string is basically just the string itself. You literally have to write print this exact long, messy string. The description is just as long as the thing you're describing. It's incompressible. And that is our formal mathematical definition of what it means to be random.
Okay, I know what you're thinking. Wait a minute, doesn't this whole thing depend on which programming language I use? Like, couldn't a program be shorter in Python than it is in C++? And that's a brilliant question. But this is where something called the invariance theorem saves the day. It proves that, yeah, there might be a small constant difference, but fundamentally, it doesn't matter. The complexity is a property of the string, not the language. It's a universal, absolute measure. How cool is that?
So it looks like we've done it. We've found it. A perfect, objective, totally universal way to measure the information in anything. It's like we've discovered a fundamental law of the universe, the bedrock of information theory. What could possibly go wrong?
Well, you know how it goes with these perfect, beautiful theories about the universe. There's always a catch. And in this case, it's a huge, shocking, mind-bending one.
It turns out Kolmogorov complexity is uncomputable. Yeah, you heard me right. It's this perfect, beautiful number that exists in some abstract mathematical space, but we can never actually write a program to calculate it for any given string. Why not? Well, it all comes down to the famous halting problem. To find the shortest program, you'd have to test every program shorter than your string. Some of those will run, print something, and stop. But some might just run forever in an infinite loop. And you can never know for sure if a program is just taking a long time or if it's going to run for all eternity. You can never be certain you found the true shortest one.
So, if we can't even compute it, what's the point? Is this all just some philosophical game? No, absolutely not. The idea of Kolmogorov complexity is what's so powerful. It's a new way of thinking, a lens that lets us see the relationships between different pieces of information in a whole new light.
For instance, it lets us talk about something called conditional complexity. This is super cool.
It asks, what's the shortest program to make string x if I give you string y for free? Think about it like this. Let's say x is the weather forecast for today, and y is the full weather report from yesterday. The program to get today's forecast from yesterday's is probably really short, right? Because a lot of the information is already there. Conditional complexity measures just the new stuff, the actual surprise in x that wasn't already in y.
And this leads to a truly beautiful result called the symmetry of information. It basically proves that the amount of information that x contains about y is pretty much the same as the amount of information that y contains about x. The informational overlap between them goes both ways. It's just a fundamental truth about how any two things in the universe can be related. It's elegant.
Okay, this is all fantastic theory, but let's get our feet back on the ground. How does this uncomputable philosophical idea actually help us, build stuff, like in machine learning? Well, it turns out this core idea, this quest for the shortest description, is the direct ancestor of a super powerful, super practical principle that's used all the time.
It all starts with an old idea you've definitely heard of, Occam's razor. Keep it simple, right? The simplest explanation is probably the best. But why is that true? Well, a brilliant thinker named Ray Solomonoff connected this to probability. His theory of universal priors basically says that simpler things with short descriptions, with low Kolmogorov complexity, are just fundamentally more likely to exist in the universe than complex things. So Kolmogorov gives us the math for simple, and Solomonoff shows us that the universe itself seems to prefer it.
And this brings us to the minimum description length principle, or MDL. You can think of MDL as Kolmogorov complexity's practical, down-to-earth cousin. It's the version we can actually compute and use. Here's the deal. MDL says the best explanation for some data is the one that makes the total description the shortest, and that description has two parts. First, how long it takes to describe your model or theory, and second, how long it takes to describe the data with the help of your model. You want a simple model that makes your data look simple.
Let's make this real. Imagine you've got a scatter plot of data. You could try to explain it with a straight line. That's a super simple model, a really short description. But it probably misses the real pattern, right? That's underfitting. On the other extreme, you could draw a crazy squiggly line that goes through every single data point perfectly. That's an incredibly complex model. It's not learning the pattern, it's just memorizing the noise. That's overfitting. MDL is the principle that helps us find that perfect Goldilocks curve in the middle, the one that's simple enough not to be noisy, but complex enough to capture the real story in the data.
And this idea of a sweet spot, a just right amount of complexity, it goes way deeper than just fitting curves to data. It can actually help us put a number on something that feels totally subjective. It can help us quantify what makes something interesting. Just picture this. You pour cream into your coffee. At the start, it's simple, right? Two separate liquids. Then, for a moment, it creates these beautiful, complex, intricate swirls and patterns. And then, finally, it all settles into another simple state, a uniform light brown liquid. Now, a physicist will tell you that entropy, the randomness or disorder, only ever went up. But we know that's not the whole story. Our sense of what's interesting, what's complex, peaked right in the middle with those beautiful swirls.
And what's incredible is that we can actually model this. Look at these graphs from a simulation. In the system where the particles are actually mixing, see the blue line for entropy? It just goes up and up and up, exactly like the physics books say. But now look at that green line. That's our measure of complexity. It goes up, hits a peak, and then comes back down. It perfectly captures that moment of interestingness that we all saw in our minds. Amazing!
And that's really the magic of it all. Even though the pure theory is something we can't calculate, the spirit of it, this idea of finding the shortest, most elegant description, gives us a powerful mathematical tool. It provides a real foundation for understanding why our brains are drawn to certain kinds of patterns, why those coffee swirls just seem more complex and interesting than either the start or the finish.
Look, these are some seriously deep concepts, and they really are the foundation for so much of the AI that's being built today. We're just scratching the surface here. If you want to keep going down this rabbit hole with us and explore the other papers that built this field from the ground up, please make sure you're subscribed to the CodeAccessHub channel. You are not going to want to miss what's next.
So I'll leave you with this final thought to chew on. If the most fundamental, most perfect measure of information is something that's literally impossible to compute, what other beautiful, perfect ideas are out there, hiding just beneath the code of the AI tools we use every day? What other uncomputable truths are secretly guiding us toward whatever comes next? Thanks for joining me.